So, in the final exam, majority of the marks allocated to the trigonometry section will be related to questions on geometric applications of trig. So basically that just means you'll be given a bunch of different diagrams with different shapes and different arrangements, probably a bunch of triangles, maybe some circles, and some squares or rectangles, just basic shapes. And these will generally be combined with the questions on Euclidean geometry. So the idea is Euclidean geometry involves all sorts of special properties of shapes as well as trigonometry, because these shapes of course include triangles, and therefore there'll be a bunch of trigonometry involved. So a good portion of the marks will definitely be related to content or cover specifically in the Euclidean geometry section. So different properties of different shapes, such as, for example, if you draw a triangle where one side of it is the diameter of a circle and then the other two sides of it connect somewhere along the circumference, then the angle at the circumference will be 90 degrees, always. They could just give you a diagram like that, and then you'd maybe need to find some of the other angles in the triangle. So that's just a simple example. It gets a lot more complicated, but the geometric applications will form the majority of the trig related questions. And then you maybe have one question which will just be word based, and then they'll just say like triangle XYZ has this angle, then find the length of this side, or they'll give you some sort of identity to prove or something like that. So the point is, it's definitely important to get familiar with the geometric applications of trigonometry because they'll form the majority of the marks in your exam. So starting off, an important thing to note is that the questions will most of the time involve working and playing around with the following rules. First of these is the sine rule, which says that for any basic triangle with vertices A, B, and C, and not necessarily any right angles or anything. So what the sine rule says is that sine of the angle at A over the side opposite this angle, which I labeled as lowercase a, is equal to sine of the angle at B over the length of the side opposite that angle, which I labeled as lowercase b, will also be equal to sine of the angle at vertex C over the length of the side opposite that angle, which is lowercase c. And the next rule is the cosine rule, which you should have also seen before, which says that for a similar such triangle, a squared is equal to b squared plus c squared minus 2b times c cos a hat. And similarly, b squared is equal to a squared plus c squared minus 2ac cos b hat. And similarly, c squared is equal to a squared plus b squared minus 2a times b cos c hat. The last one is the area rule, which says that the area of such a triangle can be calculated by saying half of one side times another side times sine of the angle opposite the third side. So that could be half of a times b sine c hat, or half of a times c sine b hat, or half of b times c sine a hat. So basically the questions will give you a specific arrangement of the shapes, and based on what information is available, you choose which of the three rules is most appropriate to use to determine whatever information the question is asking you for. And that's the basic methodology for answering the various questions you get on geometric applications of trigonometry. So I'll go through a few examples of these, of course, and they can come in two forms, either in 2 dimensions or 3 dimensions. Let's look at 2 dimensions first. So here's one question. Given the triangle XYZ shown in this diagram, with sides X and Y having lengths of 17 meters and 22 meters respectively, and angle Z hat of 19 degrees, determine the following. The length of the third side, C. So a key part of answering such questions is noting what information you have available. So in this case, we have information about 2 other lengths besides the one we need to determine, and we have the value of one angle. And so based on this, we can use the cosine rule to determine the third length. So we want to determine the value of z. So we choose the form making z as the subject, giving z squared is equal to x squared plus y squared minus 2x times y cos of angle z hat. Then sub in the values, giving 17 squared plus 22 squared minus 2 times 17 times 22 cos 19, giving a value of 65,8 for z squared, and finally 8,1 meters as the length of side z. Then the next part asks the value of the angle at the vertex y, so y hat, meaning this angle. And this time the information we have is about 3 lengths, so all 3 lengths of the triangle and the value of one angle. And to determine the value of another angle, we can use the sine rule. Since we want to determine the value of y hat, would have sine y hat over y is equal to sine of the one angle we know, which is z hat, over the length of the side opposite it, which is z. Then just sub in the values, then rearrange and solve for y hat, which comes to sine inverse of 22 times sine 19 degrees over 8,1, which comes to a value of 62,0 degrees. And is that the final answer? Not necessarily. Let's look at the diagram again. So in the diagram, we can tell that the angle at y is greater than 90 degrees. So the angle we just determined wouldn't be correct. And so to get the correct value, you take the second quadrant result of this reference angle for a positive value of sine, meaning 180 minus 62 degrees. Therefore, y hat is equal to 118,0 degrees. Then for the third part of the question, we need to determine the area of the triangle XYZ. So it's pretty clear here that we can just apply the area rule. So we'll choose a specific form of it based on which angles we already know. And we can just take the angle for z of 90 degrees since we're already given it in the question. And then you would use the lengths of x and y. So when you sub in the values, you finally get the triangle area as 60,9 meters squared. Then let's look at a second example of a two-dimensional case. So in this question we have the diagram of a semicircle with various points across it, and the center is labeled as a point C. Then since it's a semicircle, that implies that this line on the bottom of it represents the diameter of the circle. So the line XZ represents its diameter, the line CZ is a radius, the line CX is also a radius, and since the line CO is from the center to the circumference, the line CO is also a radius. Then you also have the point Y labeled, which is perpendicular to this point O, meaning it's at an angle of 90 degrees. And one angle has been highlighted, which has been labeled as alpha. So the first part of the question asks to determine the angle OCY in terms of this angle alpha. So I'll answer the question by first noting a few things. The first of these is that since CO, CZ and CX are all radius of the circle, that implies they have the same length. Therefore, we can say that CO is equal to CX is equal to CZ, as shown here. Then an implication of this is that since these two lengths are the same and their ends are joined by the line OZ, it implies that both this angle and this angle have the same value, meaning that this angle is also equal to alpha. So we need to determine this angle OCY. So since these are both alpha, therefore that means this angle would be 180 degrees minus alpha plus alpha. So 180 minus 2 alpha. So you know this angle is 180 minus 2 alpha, and we know this total angle is 180. Therefore OCY would be equal to 180 minus this angle, which is 180 minus 2 alpha. Therefore OCY is equal to 180 degrees minus OCZ, meaning 180 degrees minus 180 minus 2 alpha, finally giving the angle of OCY as 2 alpha. Then moving on to part B, in the triangle OXZ, meaning OXZ, we need to determine an expression for cos alpha. So the first thing to note is that for a triangle inside a circle where the hypotenuse of the triangle is equal to the diameter and its two ends connect to any point along the circle's circumference, the point where it touches the circumference will have an angle of 90 degrees, meaning angle XOZ is equal to 90 degrees. So since this is just a regular right angle triangle and we have the angle alpha, cos alpha would just be equal to adjacent over hypotenuse, meaning OZ over XZ. Then we can look at part C. So part C says, in the triangle OYZ, find an expression for sine alpha. Triangle OYZ. Since we know this is a right angle, we can just apply simple Socator, and therefore sine alpha would be equal to opposite over hypotenuse, meaning OY over OZ. Then for part D, it says, in the triangle OCY, find an expression for sine 2 alpha. So triangle OCY would be this triangle. And thing is, in the first part, we already determined this angle OCY as being 2 alpha. Therefore, quite simply, sine 2 alpha would be opposite over hypotenuse, meaning sine 2 alpha would be OY over OC. Then we can look at the final part of the question. Using all the information already deduced, show that sine 2 alpha is equal to 2 sine alpha cos alpha. The key to answering this question is first noticing that XZ, which is the diameter, is double the length of OC, which is the radius. Therefore, XZ equals to 2 times OC. Or in other words, OC is equal to half XZ. And from the previous part, we noted that sine 2 alpha is equal to OY over OC. So we have a term representing the equation on the left-hand side, and we need to see how to turn this into the equation on the right-hand side, meaning 2 sine alpha times cos alpha. So from the second and third parts of the question that we already did, we already have equations to represent sine alpha and cos alpha, which were sine alpha equals to OY over OZ and cos alpha is equal to OZ over XZ. I think we now have enough information to put everything together. So starting from the left hand side, we have sine 2 alpha is OY over OC. Then we know that OC is equal to half XC, so we can substitute that in over here, giving OY over half XC, which is the same as 2 OY over XC. Then we can rewrite this fraction as the product of two different fractions. So sine 2 alpha is equal to 2 OY over XC, and another way of writing this is as 2 times OY over OZ times OZ over XC. Since the OZ in this numerator and the OZ in this denominator will just cancel off, leaving OY over XC as required. And from the previous parts, we know that OY over OZ is the same as sine alpha and OZ over XC is the same as cos alpha. So we can just substitute these in over here, which gives the required answer of 2 sine alpha cos alpha. Therefore, we've shown the required identity. And you can just conclude this by saying hence shown. And that completes the two-dimensional examples I'll go through. Then for the final example of this video, I'll cover a three-dimensional example very similar to one from a past exam paper. So I adapted this question from a question I saw in the 2017 February and March paper 2 exam. and it's as follows. In the diagram below, the points M, O, and P lie in the same horizontal plane. Then LM and NO are two vertical poles. So you can just think of this as just the ground level, meaning MOP, and then LM and NO are two poles that have been set up in the ground. Then it says that LP and NP are ropes that anchor the poles at the point P. And then L and N, which are the top parts of the two poles, are connected by another rope. So that's the basic setup. And then they end the question by giving us some numbers to work with. So the distance between the bottom of pole LM and the point P is 20 meters. Then the distance from the top of pole NO and the point P is 17,2 meters. Then the angle LPM is 40 degrees, LPN is 70 degrees, and NPO is 27 degrees. And it's also worth noting that in the diagram they've also shown these right angles just to remind us that the two poles are perpendicular to the ground. And the first question asks us to determine the following to two decimal places. First, for part A, the height of pole NO. So let's see what information we have available. We need to find this length. We have one angle of this triangle, and we have one length, and we also have another angle of 90 degrees. So since we have two angles, one length, and we want to find another length, we can answer the question using sine rule by saying NO over sine 27 is equal to 17,2 over sine 90. Then simply rearranging for NO and calculating gives us the height of pole NO as 7,81 meters. Then for part B, we need to determine the length of rope LP, meaning this rope. So what information is available this time? This is very similar to the previous question where we have two angles given and we need to find another length. So while we know the angle opposite the rope LP, we don't know the angle opposite the distance 20 meters. But since we know these other two angles, we can calculate this angle, which will simply just be 90 minus 40 degrees, so 50 degrees. And in a very similar manner to this previous question, we can use the sine rule again to determine the length LP by saying LP over sine 90 is equal to 20 over sine 90 minus 40, meaning 50, which is equal to 20 over sine 50. Then rearranging and calculating gives LP as 26,11 meters. Then for the final part of the question, we need to determine the length of a rope LN. So the length of this rope. So what information do we have available? For this triangle, we know this length NP as 17,2 meters. We just determined this length LP as 26,11 meters, and we just know one of the three angles. So we have two lengths and one angle. Therefore, we can use the cosine rule to determine the other length, which in this case would be ln squared is equal to LP squared plus NP squared minus 2 times LP times NP cos 70. And subbing in the lengths LP and NP, we get 26,11 squared plus 17,2 squared minus 2 times 26,11 times 17,2 cos 70, which comes to ln squared equals to 670,30. Then taking the square root on both sides gives the answer for the question as length of rope LN is equal to 25,89 meters. And with that, we've covered the final example for the topic. I'll conclude this video by summarizing everything we've looked at. First, I start off by going through the various fundamental concepts and equations that you need to understand to go forward with trigonometry. The first of which is the acronym SOHCAHTOA, which stands for sine is equal to opposite over hypotenuse, cos is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent. Then I looked at the quotient identity, which states that tan of theta is equal to sine theta over cos theta. Next, the square identity, which says that sine squared theta plus cos squared theta is equal to 1. Then I went over the special angle triangles, which are a useful tool for knowing which values the trig functions of sine, cos, and tan would give for different angles. The first of these is the 30-degree and 60-degree triangle, which has a height of 1 and a hypotenuse of 2. And using the Pythagoras theorem, you can calculate that the base of this would be equal to root 3. Then there's the 45-degree triangle, which consists of two angles of 45 degree and is made up of two sides of equal length, making up the 90-degree angle. And using Pythagoras theorem again, you would find that the hypotenuse would have a length of square root 2. Then I went over a fundamental property of the sine and cos function, which is that the two are co-functions, meaning that the two functions have equal values for angles adding up to 90 degrees. Then I covered how negative angles can be rewritten in terms of the positive angle functions, where sine of negative angle x would be equal to negative of sine x, cos of negative x would be equal to cos of x, and since from the quotient identity tan is just a result of whatever happens with sine and cos, it means tan of negative x would be equal to negative tan x, which would be a result of tan being the result for the sine function divided by the result for the cos function. Then I covered the four quadrants, which are an important tool for knowing how the trig functions would be affected for angles between the four range of values 0 to 90 degrees, 90 to 180 degrees, 180 to 270 degrees, and 270 to 360 degrees. Where in the first quadrant, all trig functions would give a positive value, and in the second quadrant, only the sine function would give a positive value. The rest would be negative. In the third quadrant, only the tan function gives a positive value, and sine and cos on the other hand are negative. And in the fourth quadrant, only cos gives a positive value, and sine and tan are negative. Then I covered the compound angle identities, which explain how the sum or difference of two angles in a trig function can be rewritten and simplified, where sine alpha plus beta would be equal to sine alpha cos beta plus sine beta times cos alpha. Then sine alpha minus beta would be sine alpha cos beta minus sine beta cos alpha. Then cos alpha plus beta would be cos alpha times cos beta minus sine alpha times sine beta. Then finally cos alpha minus beta, which would be equal to cos alpha times cos beta plus sine alpha times sine beta. Then I covered the double angle identities, which are just an extension of the compound angle identities, more specifically the summation ones, where instead of having two different angles added together, you turn them into the same angle. So you would turn beta into alpha in both cases, which finally gives sine 2 alpha equals to 2 sine alpha cos alpha. Then cos 2 alpha equals to cos squared alpha minus sine squared alpha, which by applying the square identity and rearranging, you can rewrite it as either 2 cos squared alpha minus 1 or 1 minus 2 sine squared alpha. Then earlier on during the fundamentals part, I outlined a basic strategy for solving trigonometric equations, where when you have a question asking you to solve a trig equation within a specified range of angle values, you would use the following steps, where you first determine the reference angle, which would be an acute angle between 0 and 90 degrees. Next, you note the sign of the function value. Then based on the value of the function, you check which quadrant the function has that same sign. And this can be memorized using the mnemonic all students take calculus, or ASTC in short. Then once you've noted which quadrants the function has that sign, you determine which angles will solve the equation by learning and applying the quadrant rules for the four quadrants. Then the second case, which I covered later in the video, was the bunch of steps you'd follow when finding the general solution for a trig equation, meaning when you're not asked for a solution that falls within a certain range of angle values. And the first step would be you determine the reference angle as you did previously. Then you note the sign of the function value and the corresponding quadrants within which it has this sign, and based on this you'd apply the quadrant rules. Next, to actually make it a general solution, you have to add multiples of the period corresponding to the trig function in the question. So for sine, you'd add k times 360 degrees because sine has a period of 360 degrees. And similarly for cos, you'd add k times 360 degrees. And for tan, you'd add k times 180 degrees because the tan function has a period of 180. And in all these cases, k represents an integer, meaning a whole number, and it can be either positive or negative. Next, you would rearrange and solve for the independent variable. And then the final step is not absolutely necessary, but it's worth doing just to confirm you've got the correct answer. And that's by verifying all your solutions using the calculator. And finally, we looked at geometric applications of trigonometry, which is where majority of the trigonometry marks will lie in your exam paper. And the general approach is, for both 2-dimensional and 3-dimensional applications, first note what data you have available in the question. And based on this, you choose whether to use the sine rule, cosine rule, or area rule to obtain the solution. And that concludes the trigonometry video.